in section 6.2, number 9, they've given us this description of a volume. They say the base of the volume, or of the solid, is the unit circle. So that's described as x squared plus y squared, which is equal to 1. And the cross sections are perpendicular to the x-axis, and they're triangles. The height and the base of the triangles are equal. So from the top view, we're going to see the unit circle. That is definitely a circle. You believe me, right? It's a perfect circle. Okay, so this is x squared plus y squared equals 1. Now this allows us to solve for either x or y depending on which variable we're going to integrate with, because we're looking for the volume of this given solid. So if we looked from the top, all you would see is a circle with these cross sections through them. And they're perpendicular to the x-axis. Okay? So all the way down. And of course, since we're integrating, we'd take an infinite number of these rectangles. But in order to make this something that we can see, we could look at one of these cross-sectional areas right here. So this cross-section, this can be your base of the triangle. Okay? Now, the base of the triangle would then have a height. They don't really describe how this triangle would look, but it could come up to a point so that the base this was straight, or it could be a right triangle, so it came up like this and sloped down there. But if we looked at it in 3D, we would have something like this. If this is the x-axis, this would be the y-axis, and straight up would be the z-axis. So for our third dimension. And so they'd be perpendicular to, so we'd have this triangle whose base is like this. And then let's see if I can make a pretty 3D picture and come up like this. Right, so you'd have a triangle that looks something like this. And all of them would, so the tallest triangle would be right here across the diameter. But each one here, so we can call this our delta volume, which is equal to the area of the triangle times the thickness. And when we look at our top view, the thickness right here, this is a small interval of x. So this would be delta x. So the thickness here would be delta x. That means we have the area of a triangle times the thickness. The thickness is delta x. The area of a triangle is 1/2 base times height. And for these particular triangles, the height and the base are equal. That means we have 1/2, let's just say base squared, delta x. Now again, over here, this value right here has an x comma y value. Okay? The height from the x-axis up to the circle is your y value. And that happens to be half of the base of this triangle. So we can say the base is equal to 2y. Okay? Because half of that base is equal to y. So we can then plug this in here and we have, so this is all still our delta v. So given b is equal to 2y, we get delta v is equal to 1/2 times 2y squared delta x. Okay? Now, to actually find the volume, we need to add up an infinite number of these delta volumes all the way from -1 to 1. So all along the interval here. So we can then say, well, let's integrate this from -1 to 1 of 1/2 times 2 squared, which is 4, times y squared dx. Now this is where a little bit more work is concerned, because we have a y squared here and we have take the integral with respect to x. So we need to come back to our equation, we have x squared here and y squared here. We can solve this for y squared. Y squared is equal to 1 minus x squared. So 1 minus y squared is equal to 1 minus x squared. So that means we have 2 times 1 minus x squared dx, and we can integrate that from -1 to 1. Now, again, circles are symmetric, so we can go from -1 to 1, but -1 to 0 is the same area as the area from 0 to 1. So we can take this and say, well, this is equal to twice that area from 0 to 1 of 2 times 1 minus x squared dx, or 4 times the integral from 0 to 1 of 1 minus x squared having trouble with my paper, dx. Now, if we apply, sorry, let me move this a little bit. If we apply the fundamental theorem of calculus here, I'm going to work back this way. We can then take the antiderivative of this, which is going to be x minus 1/3 x cubed. Then we can evaluate that from 0 to 1. So we have a 4 on the outside times the antiderivative of 1 is x minus the antiderivative of x squared, so that's 1/3 x cubed, and we're going to evaluate this from 0 to 1. Okay? Now notice if we plug 1 in there, we get 0 in there, we get 0, because 0 minus 1/3 of 0 is still 0. So again, working backwards, I have that's 4 times, plugging in 1, we get 1 minus 1/3 times 1 squared, which is just 1/3. And then minus 4 times 0, which is 0. So 1 minus 1/3 is 2/3. So this is 4 times 2 over 3, which is equal to 8 thirds. Okay? So again, top view, kind of a side view, and we're going to have, the whole thing's going to have all these triangles coming through here, right? And it's going to kind of be the tallest here and then the shortest there. And that's the volume that we just found the area, not the area.